Hello everyone, my name is Somnath Roy. I'm a principal engineer in Memory Solution Lab in Samsung. So today I'm going to talk about a very specific use case of AI/ML. We call it large-scale AI/ML, where the dataset size will be at least 1 petabyte or more. Over the years, we see that compute actually grown very rapidly, advent of GPUs, new algorithm and all. But storage, specifically storage solutions, right? So it didn't go at that breakneck speed. So in fact, in the advent of GPU direct storage, NVIDIA is already claiming that bottleneck is in storage, not in compute anymore. So the question is that this large scale AI/ML that we call, right? So it can storage performance keep up with that? So I can give you one example that we are deploying this solution to one of our hyperscaler, and the requirement is basically it's 1 terabyte per second read bandwidth per rack, which is basically unforeseen. So I never heard about any storage solution till date that can serve this kind of storage bandwidth. They are running thousands of GPUs in parallel. I will talk about what MSL is doing to cater this kind of workload in today's talk. Here comes DSS, a performant and scalable object storage. So now this is a conscious decision. So object storage, because two things we have to serve. It's scale and performance at scale, right? So we choose to come up with object storage technology because that everybody agrees, right? That's the scale solution. But the problem is that whatever the object storage available today, that is not very performant. So that's why the object storage use cases are mostly into the secondary storage, not into the primary storage at this point. So our solution, our aim, I would say that to come up with a performant and scalable object storage that can perform at scale. So the right side is very brief overview of our stack. So we have a very slim library we call DSS Client Library stack that actually integrate with all those apps. And what it does is basically distributes and hide all the semantics of bucket and S3s, right? First of all, it's a S3 compliant object storage. And all those endpoints, right? So it's distribute the keys uniformly as well as it load balance, and all those complexities hides from the application. The second layer, we have that actual object storage that exposes S3 over HTTP endpoints. So and that actually underlying of that, we have our NVMe KV RDMA based very high performance storage stack. So the third layer is our NVMe KV target, that is a user space application based on top of Intel's SPDK DPDK layer. So end to end from the object storage to this target, it talks KV. And in the very end, this target stack can support both Samsung KV drives as well as Samsung block drives. So for KV, there is no transformation request. The same protocol goes all the way to the drive. But for supporting the any block drive, Samsung and any other block drive available, NVMe block drives. So that actually you need to have a transformation layer that we have that transform KV to LBA and offsets, and that actually talks to the drive. So it is essentially a zero copy transfer from object storage to all the way, and it can scale like at any level. So we tested till like in our small lab, we tested and we deployed in our customer like around 800 terabyte of storage, the solution behind that. And I have some data for that, and it scales almost linearly the back end for that. So I would now the object storage part. I will talk a little bit about that. So this is actually we took like open source Minio, and we modified Minio based on our need, along with some performance patches to get to the performance level that we want. So left-hand side is basically how stock, very brief overview of how stock MinIO works. You will say that every MinIO nodes are having their own storage. And then when the IO comes, so they talk, they exchange those slices, right, the chunks across the network between the nodes. Right-hand side, actually, what we transform MinIO into. So we basically disaggregated storage and compute, and it's basically every MinIO node can see all the storage targets available, and so actually I'm eliminating all the inter-MinIO node network transfer of the chunks. So essentially, it's like shared nothing architecture to shared everything architecture on the right-hand side. This is the main design changes. So we did a lot of performance optimization on the IO stack as well. In fact, we modified 80% of the MinIO IO stack, and then we actually open source everything, so that I have the link later in the slides. So this actually improves the object storage performance quite a bit. So now I said in the previous slides, it's a disaggregated architecture where compute and storage is actually lying on different servers. But one of the problem with that is we have to have a dedicated server for compute as well as for the storage. So that is not an acceptable solution probably for every customer, because that increases the TCO story, because it increases the cost. DSS is flexible enough to deploy in any mode. So this is one of the mode we deployed to most of our customers basically. So this is we call co-located mode. What does mean is that it's in one server we have host stack and the target stack co-located within that, and rest of the servers, when you visualize on scale, rest of the servers basically it's over the network. So what that essentially means is that for every object storage server, one of the storage server is local and rest is basically over the network. So this is such a deployment. This is on top of Dell R7525 AMD servers, so which was actually latest and which is probably even today the AMD EPYC servers. I think that's the best performance it's so far, whatever we have seen it's giving as a hardware wise. So just a little bit on that, how we deploy it. This is a very complex slides, I know, very busy slides, but I want to touch upon that because this is one of our important deployment topology that enable us to give that much of performance. So now, when we first took that server, so if you see, it is a PCI Gen 4 server. So we can put 4 PCI Gen 4 NIC dual ported, and it can support like 16 SSDs on the back end. So and Gen 4 SSDs. So when we first took the server, we wanted to see that how is that good enough to give like saturate 4 NIC dual ported NIC performance, which is essentially, if I take the 100 gig NIC, so it will be like 24 into 4, 96 gigabyte out of a single box. And then if we take that storage, right, we have 16 Samsung PCI Gen 4 SSDs we put, so that each one can give around 6 to 7 gigabyte performance. So eventually it is 96 to 100 gigabyte at the storage level. So when we run our regular FIO and iPerf and all those tests, RDMA, even the RDMA tests, so we saw that even it's not able to saturate the NICs. It's not scaling 1 NIC to 4 NIC, 1 drive to 16 drive. It was not scaling. So we dig down and then we studied AMD architecture and we found that it's quite a different beast than the Intel that we used to work with. So we found that there is an option. We can, they're flexible enough. We can select the number of NUMAs you can create within a socket. So this view is basically it's a dual socket AMD EPYC. So each of these purple box is one socket. So now we start to play with these NPS settings of AMD, and we found that if we create like 4 NPS per socket, which is total 8 NUMA sockets, so hardware is giving the best performance. So we in fact able to get the hardware performance like around 196 gig for the NIC, 100 gig for the 96 to 100 gig for the drives. But this kind of settings pose severe challenges on the upper stack, like the application stack, right? So 8 NUMAs, how you actually affinitize your stack? So that's a huge challenge. Even what we used to do in say Intel machine is a 2 socket, one you are running. But this kind of architecture, we had to actually a lot of redesigning, lot of tuning needed to actually tune for this particular platform. So this is some of the things we did. So also what we notice is that in this AMD cross socket performance is like cost. If you have your IO going cross socket, so the performance is really bad. It's impacting the performance like anything. Within a socket, if you do a NUMA cross NUMA, so performance is degrading but not that much. And if you carefully look the architecture, right? So now I put it like, say, if you see, it has like 4 NUMAs on that, and I have shown that where the drives and NICs are. If you see, like socket 0, NICs are on, it's a dual ported NIC, so it has 4 NICs. So NICs are NUMA 1, NUMA 2 on that socket, and if you see the drives are on NUMA 2 and NUMA 3, 8 and 8. So the hardware itself, it will be crossing the NUMA. There is no way we can get around that. In the other socket, it is even worse. If you see NUMA 5, all the 8 drives are there, and then NICs are on NUMA 4 and NUMA 7. So it's bound to have some kind of inter-NUMA traffic. So and another important point is that if you actually divide the entire system with 8 NUMAs, each of the NUMA is now entire system memory bandwidth is divided on this 8 NUMAs. So like if you have 240, 250 gigabyte across the system is gigabyte per second, the memory bandwidth. So each of these NUMA will hit like 240 divided by 8, like say around 30 gigabyte. So, those are actually observation. So now we put our stack like this. So we first thought of like putting, we first created on the target side 2 subsystems. That's the SPDK subsystems. So but we have actually created pool on top of SPDK subsystem. In the stock SPDK, it's a 1 drive 1 subsystem. Here we actually modified that our target, so you can create a pool on top of subsystem addressing multiple drives. So we created like all those drives on the socket 0, one subsystem, and socket 1, another subsystem. And then we are running 4 object storage servers, so 4 on each of these NIC, affinitized on that particular NUMA, all the way. So this is good. So this way, actually, when we run individual storage size, all our CLIs and other things, it's giving pretty good performance. I have some numbers later to talk about. But the moment actually put our object storage servers, so even if we do all this optimization, our object storage server still has some copies. It has like around 4 copies. So now if you think like, so if it is giving say like 9 to 10 gigabyte on each of these server, 10 into 3 or 10 into 4, it's stretching like 40 gigabyte for the software itself on that particular NUMA, which we think that was the problem when we ran all without object storage. So it was not going beyond that performance because it's stretching on that NUMA bandwidth that I talked about. So what we did is that so we ran our object storage and the host software stack with memory interleaving mode. So it's basically sharing the NUMAs or the neighboring NUMAs. So for example, on object storage server 1, like Minio 1, in this case, is sharing on is running on NUMA 0 and NUMA 1. Similarly, Minio 2 is running on NUMA 2 and NUMA 3, and then other socket is also similar way. So this way, basically, it is getting 2 NUMA memory bandwidth, and that limitation went away. So, and we got a pretty good performance out of that end to end. So this is the DSS client wrapper that I talked about, the very top layer of us. So as I said, right, so it basically exposes simple get, put, delete, and list kind of APIs. And it hides all the S3 semantics. No bucket, nothing you need to worry about the application. Also that so many Minio endpoints, right, or S3 endpoints. So it will actually do distribution, load balancing, cluster expansion, cluster shrink, all those things actually it will take care. So this is our actually, whatever I talked about right now, this is at scale, the overview of how we actually deploy it. The bottom part is our stack, right? So if you see, it's a co-located deployment. So each of these cluster having Minio 1 to 4, which is our object storage, and then the target. And like that, we deployed n node cluster. So one of these target or the storage is actually co-located on the local, and then rest of this rest of the storage is remote for this object storage server. And then the top end we use DGX, and then we ran AI application like PyTorch training and all, and integrated. We have integrated our DSS Client Wrapper with PyTorch, and then it eventually talked S3 to all of our storage. So this is the deployment view. Now let's talk about some of the numbers. So let's first talk about the deployment and the setup. So we the same way that I explained, right? We created like 10 node cluster, and each one is R7525. It's a dual socket 64 core CPU. Each one has 1 terabyte of memory, and we have like 4 Mellanox dual ported 100 or 200 gig. So at this point, we're not able to saturate 200 gigs. So 100 and 200 is giving the same performance. And then we have 16 PM 1733 4 terabyte Gen 4 NVMe SSDs on each of these server. And total data set we generated around 400 terabyte for this test. Now you see the top chart, it's just the backend data. Backend means it's not from the object storage end to end. Not that it is not doing any S3, but our KV, our NVMe stack that I mentioned, right? So that stack performance it shows. So each of these server, it's giving like around 44 gigabyte per second, which is basically pretty close to saturating the NIC performance on that. Because it's a dual ported NIC, we gave the backend for the backend ports, like one port of this each NIC for the backend and another port for the front end. So that way I'm saying it's pretty close to saturating that. So 44 gigabyte each of this node, and it's scaling till 10 node, like around 440 to 450 gigabyte. But if you see the below one, which is with our end-to-end, and we use S3 benchmark, which is the open source S3 benchmarking tool. So with that, if you see like 1 MB, this is basically 1 MB performance on that. So 1 MB object size, and if we enable the erasure coding, we are getting only like 170 gigabyte per second, 170 to 180 gigabyte per second. If I have an object size of 2 MB, it bumps up to like 270 to 80 gigabyte per second. And then similarly, if we have 1 MB without erasure coding turned on, we are getting the same like 270 to 280 gigabyte per second. So as you can see, right, so end to end is not able to saturate our backend performance yet. So this is our generation 1 numbers. So I'll talk about more what actually it's coming to address these particular issues. So even before that, why actually that number is low? So we think that the 4 copies I was talking about is still in the object storage layer. So we think that that actually causing the degradation. It's an obvious thing, right? So okay. So before going to how we address that, so I'll go with some other problem that we are facing. So now we have a storage solution that we think that okay, we able to get a pretty good performance out of that and at scale. So how to prove that to the customers? So we then think of like, okay, we'll create that much of data set, not 400 terabyte, around 120 terabyte or so image. We it's just the image replication. We didn't care about what exactly the image. We got a data set, 120 terabyte data set. We didn't find it. So we got a small like 2 terabyte, 4 terabyte data set, and then we replicate that to form a like big enough data set, like around 120 terabyte or so. And then we ran basically a training based on PyTorch. Both that data, putting it in an NFS as well as in our servers, and we didn't see any performance improvement. So we want to know what is going on, and we are all new at the AI world. So we are the storage guy. We don't know anything what these tools does, but for the sake of this proving our point, we have to do that. So we dig down, and what we found is that after reading like PyTorch data loader, after reading all those image, they do a lot of other stuff. For example, decoding, they do transformation, and they form the tensors like that, right? So all those things basically, we saw that, okay, that's the bottleneck. Because even if you are reading faster probably, but those guys actually slowing you down. So we wanted to know that, okay, if there is any storage benchmarking solution available for AI training, like say PyTorch, if they have anything, or anybody written like any tool that actually showcase the storage performance while running the AI training. We couldn't find anything. So what we decided to write on our own. So this is the AI benchmarking tool. So what we did is that we took the PyTorch data loader and we created a framework around that. The framework means like you can put hooks within that. PyTorch provides that all those interfaces, and we modified that. We didn't modify the PyTorch framework, so we created a framework that we can actually put our own class. Like say we can put a dummy training class which will actually load the n number of batches, and then say that, okay, report how much actually it took to load those many batches. Similarly, like we are putting stats around that. Like, okay, so if you run end-to-end training, this much of time it took to load data, this much of time it took to pre-processing, this much of time it took to do an end-to-end training, like that. So, so this is. Oh, I don't see. This is actually a demo. I don't see this cursor coming. Okay, anyway. Oh, it's running, sorry. So this is actually a configuration file of this tool. So where actually, as I said, right, we can write our custom dataset class, custom training class. Also, it takes like the storage, whether it's running from file system or it's running from S3. Left-hand side is the file system, right-hand side is the S3. So, and you give the parameters, like in case of file system, you give the mount points of file system, and for S3, you give the prefixes that actually needs to load data from. So, and then it, along with other PyTorch framework parameters, right? So it will take like n number of batches, I said, right? So you say that, okay, you have a 120 terabyte data set, batch size is 100. You can say like you load 10,000 batches and then stop, and then give me that time or bandwidth it got from the storage to load that many batches. So that's it. So now if you run it in that mode, like one is running file system, another is running S3, it will report. It will first do a listing of all the data, and then it will actually load these n number of batches. I think in this case probably 1,000 batches it is loading, and then eventually it will report the bandwidth out of that. So it is pretty close to how people will be running training, because we didn't modify anything the way PyTorch runs, but we just created a wrapper around that, so that actually we can showcase the storage benefit, storage performance benefit. That was the whole purpose. So now with that, we actually ran with this tool the same data set, but we actually this time we created 6 node cluster, not 10 node. And the main reason is that we don't have that many servers so at this time available. So we created 6 same server setup, and we use the same server for NFS. This is the standard NFS, by the way. So NFS, we put the same data, and we put the data on the DSS S3. And we saw at scale, right? We are increasing the number of clients in the bottom, and at the 12 client case, right? Even it's better all the way. In 12 clients case, it's seeing like at least 3x performance better than standard NFS server. Okay, now going back to why the performance was low, why we are not able to saturate that storage performance. So this is like, I will not go through entirely, but this is basically the path of our DSS object storage to all the way to the target, the intermediate call. And the red letters are actually the copy. You can see that 4 copies are happening in this case. And we think that's the bottleneck for our current solution. Now, what's the way out? So what we did, we actually, we have a patent pending application, patent pending technology, which is we called S3 over RDMA. So what we did is that we are still collecting the S3 request from HTTP, but while returning, we are actually returning to the end client all the way, bypassing entirely object storage path. So with that, basically we obviously removed all those 4 copies, and performance actually was much better. So this is our Gen 2 solution, by the way. So with this, now we have something basically, because RDMA is needed for our next step, which is basically GDS, GPU direct storage. So now we got some benchmarking number from NVIDIA Foundry. So they actually published this number. So on GDS.io, unfortunately GDS.io tool is not open source, so we couldn't actually hook into that. But we try to replicate the same number in our setup. So 2 numbers are CPU to GPU. That means basically first actually the data will be RDMing into the CPU memory, and from there CPU memory they will be copying into the GPU memory. So that was their old solution. Now for GPU direct storage, which is basically GPU, so it will be directly RDMing, the storage will be directly RDMing to the GPU memory. So that's why you see the performance bump, and you will see that with one node they are getting like close to 72 gigabyte or something with this tool. So okay, so this is basically with BeeGFS. So that's the open source, very popular distributed file system. So they use on top of NetApp storage to replicate that to produce that number that I showed last time. So this is how actually we don't have NetApp box. So we use the same 7525, but it's the same way. This is actually the way they reproduce. So they use like 2 nodes for their BeeGFS server and 2 NetApp boxes for their NVMe over Fabric storage. So we use similarly like 2 7525 we use for their services, BeeGFS services, metadata, and then on the 100 gig connectivity we have NVMe over Fabric storage on the other side of the network. And then we tested with 2 DGX. So that's the same way basically they ran. They are also running with the 2 DGX. Wiring and everything is similar, all 100 gig connection all the way. And then we ran same GDS.io tool in our case. So and it's pretty much actually simulated the same data that they produced. One extra thing we added, and GDS.io has that option, just to do a CPU. It's not CPU to GPU. Obviously, CPU to GPU has a copy. So we wanted to see that if we directly send it to CPU without copying to GPU, what is the performance? So that numbers also we collected on that, which is like which is basically with 2 DGX servers around like 48 gigabyte or something all total. And then the GDS we ran, that is basically same at around 72 gigabyte. So now we wanted to do the same thing. Instead of BeeGFS, we put DSS in between. And we use basically same 4-node cluster. So, but we don't need any metadata and all, it's a solution, right? So we use all 4 for the storage. So which is, you can say, is a good TCO story. We can use most of the stuff for our storage solution. There is no dedicated metadata servers and all those things needed. So we use that same 4 servers and the same connectivity to DGX and all those things. But we cannot run GDS.io because GDS.io is not open source. We cannot hook that in. So what we did, we ran this same AI bench test. Now AI bench, if you see, right, so it can run over NFS or any file system mount point, here in this case BeeGFS, and then it can run on S3. So we ran same AI bench test result. And for DGX, we got up to like the same setup, we got for 56 gigabyte per second versus 46 gigabyte per second. So that's actually pretty unfortunate. So, and we found out that one of the socket of DGX is running always lower. We couldn't figure it out why at this point, but the tool itself has some overhead because it's a Python tool. When you run for like threads, it's not a thread, it's a process, and it creates so many connections. But then we are asking that, okay, if that is the case, why one socket will perform low? Why not the other socket? So DGX is very complex architecture, right? Even if it's an AMD, they put a lot of other stuff. They have like 8 other NICs also available on that. So we are yet to find out why. So, but to test that, okay, is it really a DGX problem or it's our tool or our stack problem, right? So we ran it on the similar machine on the Dell AMD clients that we are using, right? 6525 is another client that is pretty similar to the DGX NIC setup. So we ran it on 7525, which is like we are using as a storage, as well as 6525. And we got like much better performance. We saw all the NICs sockets are performing much better. But BeeGFS performance increased only 2 gigabyte, but we increased quite a bit on it's around 55% improvement. And the other bottoms are the CPU usage, which is like, I would say, pretty similar on that. Here actually it's more because it's producing more data, more throughput. So is that the limit? So we wanted to check. Now another set of thing we did, like we ran S3 bench. If you remember our like initially we ran, right? S3 bench is our end-to-end benchmark, open source benchmarking tool for S3. So we ran that, and with the same setup on DGX. This time DGX didn't have that problem on the other socket. It's even, in fact, it's performing much better than 7525. So again, that's a mystery to us. So we are working on to resolve that. But see this performance with these two nodes, we're able to get like almost 88 gigabyte per second, which is basically each one is giving 44 gigabytes. So that means we are pegging the network performance in this case, 100 gig network. So we are yet to put 200 gig and see how far it can go. But that's the case. Now, if we compare that to GDS.io, we think that GDS.io is pretty comparable with S3 bench, even if it's a different tool, because it's just point to point. It's exercising the storage performance, right? So we saw that, if you remember the other data, right? So it's a CPU. If you see the CPU performance, that is actually pretty comparable to us, because we are also RDMing from Gen 2 solution. This is by the way, it's a Gen 2 that RDMing directly to the client side. So that is also RDMing to the client CPU, and GDS.io also doing the same CPU. So if you see that 80% actually improved on the performance side. And if I compare the GPU number, which is 72 gigabyte, we are still above that, not going directly to the GPU, but with the CPU. So the next step actually we're working on is we are trying to work with NVIDIA to get GDS.io source code, so that actually we can see that, okay, if we can get the same tool performance. Also, like they have a DALI library which actually support GDS, but it's a different PyTorch application altogether. We try to hook in our DSS client library there and the DSS stack to see what is that, what it looks like in future. So that's it on the numbers. So it's all open source. Whatever I talked about so far, everything is open source. So it is under umbrella DSS, and we have DSS SDK within that has our storage stack, that high performance NVMe KV that I talked about. That will be part of that. We have full Ansible DSS Ansible based deployment, which is part of within the DSS Ansible. So it's a fully automated deployment that is also open source. The DSS Minio, that all those enhancements I talked about, that is also open source on there. And then within the DSS ecosystem, we have this client library, this AI benchmark tool, and along with even the SC benchmark, we did some modification that is also part of that DSS ecosystem. So that's it. So, and okay, I think we have time. So any questions on that? No questions? Too much data? Yeah. Right. So that's a good question. So the customer we are working with, they have like 1 to 8 megabyte range. So we wanted to do the lower end of that, which is like 1 megabyte. So everything, the data that we produce so far, it's all 1 megabyte, because we think that the lower the object size, it will stress your object store, right? Because more IOPS, the higher is probably much easier. So 1 MB is the object size for all those data. Okay, so if no other questions, thank you. Thanks for listening.